How does the resistance of a filament bulb vary with the amount of current passing through it?
I said, how does heat affect the magnetic properties of a magnet?
What did you do?
Right? Yeah.
What'd you do?
Magnetism.
Thermodynamics.
Well, we're learning about it right now.
Yeah, that's why I don't know what I want to do.
Or you could do actually low key. Everything we have here is kind of simple.
Thermodynamics.
I was trying to do some of the pods. They're not that hard.
Wait, the first pod was so easy. It's just the density equation plugged in.
If you have notes on thermal energy, temperature, density, things like that, I'll check them here in just a minute. If you missed your test, we can get that started here soon as well.
Someone's at the door.
Sean, you need to finish your test. Get it going now.
Oh, you did the table too, like I did. It's like low-key, like everything that you kind of know. It's like kind of intuitive. Like gases have no pattern. Yeah. We're locked in for this one. That's what happened last time. They happening again. That's crazy though. That'd still be a 3 on the 8 on the IB set. What I got him at this. I don't like saying it out loud.
Nobody's gonna be like, oh my god, an idiot, he's an idiot.
I had an oh my god reaction, not an idiot reaction.
I think he said the average was like 40 or 50.
This is one thing.
Like I know I could have done better.
No.
There are 3 forms of kinetic energy.
Rotational,
Transitional and vibrational.
oh yeah, and that's in only gases. I'm pretty sure. Or no, wait.
Vibrational is in solids, transitional is in liquids and gases, and then rotational can be in either.
Yeah, so it's solids and liquids that can only have it, but I know gases can only have like potential energy or something like that.
The internal energy of a substance is the sum of the total random kinetic energy and the total potential energy of a substance.
Oh wait, sorry. Gases only have kinetic energies. What? What did I say that? I said it towards the back.
Alright, taking notes, taking notes.
I know they can have potential energy.
No, this is gonna put this to the inside. I want to see if you can forget about it.
Oh. I'm gonna like have to flip it to show more. Listen, actually, I could just do it like this. Just think of one right now. You know I did, right? I just want to change it to two.
Yeah, no.
Give me some good ones. And then I low-key changed mine a little bit.
I'm asking.
Good idea. I think today's lesson is quite easy.
I think we'll have enough time to finish the pause. Hopefully.
1 through 15 odds. It's like what, 7?
Yeah. 7 or 8. 1, 3, 5, 7, 9, 11, 13, 14, 15,
It ends on an odd number.
Wait, like 1 is so easy. 1 is like you can just play it into calculator and get the answer instantly.
Although I think they try to trick you by because you have to do something. You have to convert it differently since it's so instead of moving it 2 to the left, you have to move it
For the sig fig?
6 to the left.
For like when it's like whatever times 10 to the power.
Yeah, converting centimeters into meters. You have to move it along. Centimeters cubed. And when it's cubed, you have to do it.
That's like the one confusing part I hate about it.
I didn't know that today.
It'll say like something to the power of 3, and then it'll like on the answered one it like this. So you have to check. The conversion's a bit tricky. Most of the time what I do is I just in the answers I just get the answers like totals, and then I get my total and match it. So I just plug everything together.
Good luck, ChatGPT. They don't know.
Oh, using school. Yeah, that's good. I was about to say how would it
Arden, cool it. Our dad joke for today. Why did Leia change her hairstyle on Hoth? Huh? You're on the right track. She was freezing her buns off.
I don't think he actually knew it.
She actually only had the buns hairstyle in the first movie. Alrighty, so a couple of announcements before we get started into our lesson for today. One, I did update grades with your test scores. Keep in mind we do have a new curve for this year, which I posted on rooms. And you should always be checking rooms because you never know what I'm going to put on there. I also put in announcement using AI for labs specifically. And since we are starting our AI journey, our IA journey minus the AI, it would be very beneficial for you to I would leave AI out of it until maybe like you write your rough draft, and maybe like you can ask AI to grade your IA using the rubric from IB and see what it says. See what things it may suggest you to change and update and things like that. But remember, AI is not a replacement for our work, but rather it is a helper and a tool for us to achieve our work. Okay, but our work needs to still be our own. So as you graph things and analyze your data, that needs to be your own stuff. Sure, you can use a computer-based software like Excel or Desmos or something like that, but you still have to plug in the stuff, and you still have to tell the computer how to process it. Okay, so that's going to be one of those things that we are looking for as we look at your IAs. I have to think about it now because AI and IA are
Inverse.
that. So, also, I have a dentist appointment, so I'm going to be leaving at about 2:15, and there will be a sub to watch you guys for the rest of the class. So. Yay, dentist.
Okay.
Yes, Troy.
I think the last time I lost you were measuring
I do. Yes, I do. We can field any specific questions about what I might or might not have in the lab for your IAs later. Yes. We're gonna have to break that back out. Okay. Pardon me a minute. I'll be right back. The IA schedule. Your research question is due today, so make sure that you make it testable. So it should be, how does this affect that? Some things that you can measure both sides.
Crazy cameo. Yeah, I never thought I would ever see her here in the science building.
Their classes on the other side of this
School. Yeah. It's hard.
I guess we just email it to him.
I'm sorry, Mr. Freshman.
How do we turn it? Are you gonna ask how we turn it in?
Alright, can we just email the research question to you instead of like writing it down?
Yes.
Yes, sir.
You may email the research question to me. That would be acceptable.
Okay.
Instead of having to write it down on a piece of paper.
I'm going to write it down.
Yep, that is acceptable. All right. Were there any other questions?
Oh yeah, I'll look at what people on.
I'm gonna know what my IMG,
The topic? Okay.
what kind of.
Well, you can write it down along with your research question.
You got food mark?
Okie dokie. So, we are transitioning. So we were in topic C3 last time, and now we're going backwards into B1. Okay. So we'll actually hit all of the B topic this year, but each one is going to kind of be its own chapter. Although I think I did combine the B2 and B3, but B1 is definitely its own chapter. So we'll be here for I think five lessons. Yeah. So 5 lessons in B1, talking about heat and thermal energy and all of that fun stuff. Most of the stuff that we'll talk about today is actually pretty base level, which is good. It started off talking about the solids and liquids and gases and density. So density is our first equation here. Keep in mind that IB doesn't give you a legend or a key that shows you like what the variables mean in our equation. So we just kind of have to know those. But remember, this is actually rho. It stands for the density, or more specifically, the volumetric density of a substance. And I say volumetric density because you can have other types of densities as well. Like if we take the mass divided by the area, like if we were trying to find out the surface density of like a piece of paper or something like that, then that would be surface density. I forget what symbol they typically used, but it's not actually in our equation sheet, so it doesn't actually matter. And then in the AP Physics C class, whenever we're talking about the center of mass, specifically with an object that has a non-uniform density, as in, like, let's say we have like a block or like a piece of wood, but different parts of the wood are denser than others, and so your mass center isn't actually in the center of the object. It's actually been shifted over to one side or the other, which is cool stuff. And if you actually the only one person that is in the APC that's also in this class isn't here, so it doesn't matter. But we also have mass per length, like we actually talked about that when we did vibrations and strings and the music stuff from last class, from the last year. So like the thicker guitar strings versus the thinner ones. This is a linear density, which I do remember is lambda. So there are different kinds, but this is definitely the volumetric, or the, if you were just to say the density of the object, then it's most commonly known as this. Okay, so the volumetric density, or just the density mass divided by the volume. So not really a whole lot of stuff that we need to talk about here. However, when it comes to doing problems and converting, okay, so usually your density will be in kilograms per cubic meter, okay, but you may have to convert from like grams per cubic centimeter. Okay, so we know easy peasy to convert from grams to kilograms and back again. It's like 1,000. You either multiply by 1,000 or you divide by 1,000. But not so easy with the centimeters to meters. You would think because because 100 centimeters is equal to a meter, then it should be that 100 cubic centimeters is equal to 1 cubic meter. That is actually not true, okay? Because we would have to basically cube both sides. So it's still 1 cubic meter, but then this is 10 to the 6 cubic centimeters. So watch out for when you convert, make sure that you are using the proper relationship as we are converting. And you can always go back to the basic one and then apply your exponents as well. So this will also work like with square centimeters and square meters. Cool, so density. Yep. We're going to, so this kind of ties in. Last year when we talked about the buoyancy of objects and how they float, and objects float or sink based on if they are more or less dense than the substance that it's in. So like we sink in the pool of air that we call the atmosphere because our bodies are more dense than the air, okay? But a helium balloon would actually be less dense than air. That's why it rises up there. Also, same thing like if something floats in water, okay? Which a human could float in water if you like inhale and then you hold it. You are now expanding your volume because you are holding a breath in, and that'll actually help you to float easier if your body is not made so that you can't float that well. But the larger the volume per the mass, that is going to give you a better time to float. I cannot float that well. They do have a table of different densities of things on page 178, so you may need to look that up as you do your pods. Okay, and again, your pods are 1 through 15, just the odd ones. Temperature, so the book talked about thermal equilibrium, where two objects are in contact with each other, as in if they are at, so when two objects are at different temperatures and they're in thermal contact with each other, then heat will transfer and the flow of energy will occur going from hot to cold. So like if I hold an ice cube in my hand is going to give away the heat and it's going to be absorbed by the ice cube. And assuming that I am not a homeostasis, a creature that does homeostasis, as in maintains its own temperature inside of its body. So like mammals, we do that. Reptiles do not. They're cold-blooded. They cannot maintain their own temperature inside of their body. That's why they need to be exposed to sunlight, and that's how they warm themselves up. So heat flows from hot to cold. We'll talk a lot more in detail about that in the future. But the idea here is that these two things that are in thermal contact with each other that are in different temperatures, they will equalize. So when they are at the same temperature at the same time, they are in thermal equilibrium with each other, and therefore heat will not flow because there's no change in the temperature. There's a cool graph on page 179 showing you a hot object and a cold object, and they will approach the same temperature over time. How quickly that happens, well, that's another lesson. So this is really just like an intro to the rest of our chapter here. In terms of the temperature scales, we should know some basic things about the Celsius and Kelvin. our equation, we do have a conversion. It's not actually in the B1 section, but if you scooch over to the front, let's see, where is it? So it's in page 4. So right below the multipliers, like the metric prefixes there, we've got some unit conversions, and our temperature scale is on there. So easily we can use that to change from Celsius to Kelvin. We do not need to know how to go from Celsius to Fahrenheit. We don't need to know that, but we should know that because the equation is so easy for the Celsius and Kelvin, that comes from the fact that the degrees Celsius and the Kelvin are actually the same size in terms of change of temperature. The Fahrenheit degree is actually a lot smaller. Okay, so like for example, we should know things like the boiling point of water and the freezing point of water, and like absolute zero, based on let's see, Celsius and Kelvin, and then we can play around with the Fahrenheit real quick. What do you know so far of this list? The boiling of, okay, where? Fahrenheit. Is what? No, that's Celsius.
Kelvin is 373.
Kelvin is 373 because we're going to add 273 to our Celsius. Technically, it's 273.15, but we're just going to ignore the 0.15 because it's usually not going to be that important. Hello. Yes. Oh, excellent. Okay, so this is typically where we'll be, and let's see here. So the idea here is you want to film me and the screen, but without getting the rest of the student body in. Okay, cool. So actually, if you just because this right here is free, so you can just park yourself there and you can see things without getting the students in.
Okay, yeah, this is what we'll be using, so
Okay.
I think I'll have some settings on it, I just haven't checked it out yet.
Okay.
Other than that.
Mm-hmm.
Yeah. So typically I'll be on the board here. We may have some questions that we show up on the screen, but this is the center of my space.
Okay.
I've been doing this for 3 years.
No.
What did you even do? Oh.
I was expecting it. So.
What?
I've already
Oh,
been
you're
doing
welcome.
What's your name?
Maynard. Yeah. Thank you.
Nice to meet you.
All right. So do you know when you'll start?
Wednesday,
Okay.
but I'm not sure if it's A day or B day I'm scheduled to see. So.
So he's in this class, so you'll see me on videos.
Days?
Yeah.
Today's A day?
Today's video.
Today's B day, so
Yeah.
Wednesday.
Yeah, Wednesday. Okay, cool.
Yes, sir.
Excellent. All right. Back to work.
Sure.
I thought that was my sub that was early.
I thought so too.
So FYI, that's going to be, he's going to be in here recording our lesson. It's one of the accommodations for one of our students who happens to not be here a lot of times. So that's why he's going to be here, and he should be here every class period, filming what happens on in class. But he's going to do his best to not get you on the screen. So just me and what I show. Okay. All right. So back here. So the boiling is actually 212 Fahrenheit. Okay.
Oh, you said that,
Freezing
right?
point is 2 degrees.
Zero.
0 Celsius.
273.
273 Kelvin. And the absolute zero, of course, is the zero for the Kelvin because Kelvin is the absolute scale. That's Yes.
Negative 270.
Negative 273. Yeah, it is.
And this is what, negative like 400 something?
Yeah.
Something?
400 unknown.
400-ish. Okay, there we go. But again, we don't actually need to know that, but we live in America and we use Fahrenheit, so
Disgusting.
why would we ever need to use it? Just conceptually.
Oh.
Yeah. Cool. Alright. So we've got the basic equation that we can go from Celsius to Kelvin and back again. And really the last thing that we need to talk about is the microscopic view of temperature. So there is another equation here. If we go back to our B1. Let me clear some space here. Okay, so E, so K, E stands for what? Energy. K is
The whole thing is
kinetic,
kinetic.
R means
Average.
average, yes. Alright, so this is going to be,
Oh, this is the average kinetic energy
KE,
equation?
that's
Yeah.
just a constant, that's the Boltzmann's constant, which we can look up in the front, times the temperature. Remember, anytime we have a temperature in an equation, it must be in Kelvin. Okay, so in here, in our gas laws equation and other things that we have our big T as the temperature, it's going to be in Kelvin, so we may have to convert if it's given to us in Celsius. So what this means, and we kind of all know from past science courses, is that the temperature is a direct result of the motion of the particles inside of the object. Okay, guys? Thank you. So when we're talking about, okay, well, this table is at a particular temperature. I can measure it using a thermometer or an infrared BB thing, okay? And I can say, okay, well, it's at a particular temperature. So the higher this is, the greater the average kinetic energy of the particles. As in, if we were to see inside of the table, and we were to measure the mass and the velocities of all of the particles that make up that table, which, I mean, there's like trillions of things in there, right? So if we were to calculate the kinetic energies of all of those things, and then take the average of all of those kinetic energies, right? Because some things are going to be going faster, some things are going to be slower, but we're taking the average of the kinetic energies. That's what this gives us, okay? So this is also what we call internal energy, okay? So like a substance is going to have a certain internal energy based on the temperature. And of course, as things warm up or cool down, then that's going to change, okay? And really, so like, if we go back to the whole like ice cube in my hand example, right? So I know that my hand is warmer, so the particles in my hand are moving around faster. Now, granted, my hand is mostly a solid, so it's not like these things can float, okay? But the ice cube is on contact with my hand. And so the particles of my hand that are in contact with the particles of the ice cube, those guys, there's constantly collisions happening. And so the faster moving particles of my hand are impacting the slower moving particles of the ice, and eventually the transfer of the energy in the collisions, because they will not be elastic, okay, is going to transfer energy from my hand into the ice cube. So that's really what's happening. The particles inside are colliding with each other on a large scale so that the temperature of one object actually changes, which is cool to kind of think about. So the hotter it is, the more temperature, the more average kinetic energy that we have. But we have, let's say that we wanted to find, okay, well, what if we could calculate what the what the average speed of the particles could be. Like, and this is especially useful when we talk about like an ideal gas, okay, which we're going to talk about gases more throughout this chapter. So if we were to go backwards and say, okay, well, if this was equal to the average, so basically the average is going to be, we're adding up all of the kinetic energies of the particles, and we divide it by the number of particles that there is. That's how we take an average of things, right? We add them up and we divide by the number of things that there are, okay? So that's what really this is we're adding up all of the little tiny particles kinetic energy. Now, if we were to break that down, that's going to be, okay, well, 1/2 the mass of the particle times the speed of the particle squared, still divided by the number of the particles, because again, we are adding up all of those things. Let's assume that all of the particles are identical, as in an ideal gas. Like we only have oxygen, or we only have helium, okay? So then the mass of each thing is actually going to be a constant, right? And so we can actually factor that out, and we can say, okay, well then this is really like 1/2 times the mass of the collection of the particles, so I'm going to call that big M, times the sum of the speed squareds, okay? And eventually we get to the part where we're trying to find out, okay, well, what is the V here, okay? So I might have confused it a bit here. Let's kind of go back. Yeah, I confused myself there. Let's go back to our average kinetic energy. Okay, that's average, not a vector. So if we were to break this down, this is going to be 1/2 times the mass times the, basically it's the average of the square of the speeds. Because assuming that we have all of the same mass thing inside of it, okay? And then if we were to solve for V here, okay, I would get something like this. So the V is equal to the square root of T2 times the average kinetic energy divided by, actually the average mass would be the small mass of the particle. I apologize. That should be small m. It's been a long day, y'all. Sorry. So in terms of, so this would be the average speed of one of the particles in that substance, okay? But because it's based on the average kinetic energy, I can't just say that this is average speed. It actually has a special name. It's called the root mean square speed. Root mean square. Root mean square speed. Because it's really based on the average kinetic energy, because how we find it is we have the root of the mean, the average of the energies. So this is not actually in your equation sheet. It might show up sometime because it's a common thing that we see in IAB physics. So the root mean square speed basically is like the average of, is like the average speed of the substances, or average speed of the particles inside of a substance. Okay, but I can't just do a straight. It's not just the average, but we call it the root mean square speed because it's based on the average of the kinetic energies. Okay, so again, that's something that is not in your equation sheet. It might be useful in one of your pods, but that's how we find the root mean square speed. In the past, this has been on the IB equation booklet. but now it's not. So, but just in case it does happen to show up with your pods, there you go. And that's about it. So next class we'll actually talk about conduction and convection and other types of thermal energy transfer.
Was the average kinetic energy.
So, yep, that's it for today.
These are really
You guys have your pods. I
didn't
believe
see
your
them.
quiz is
I thought it
already
was
online.
It's not.
It is excellent. Yes, I thought I did that before. And yeah, so feel free to take 5, and then we can spend the rest of our class time, which is a lot, working on our pods and our quiz. Yes. 6.